Look up at the night sky on a clear evening, far from the glow of any city, and you will feel something that no other species on this planet has ever felt. Not just wonder, not just curiosity, something older and stranger than either of those, a pull. A gravitational tug that has nothing to do with physics and everything to do with who we are. Every human being who has ever tilted their head back and watched the stars has felt, on some level, that those lights are not merely decoration. They are destinations. They are places we are supposed to go. This feeling is not rational. The stars are incomprehensibly far away. The distances involved would shatter any intuitive sense of scale. The nearest star system beyond our own, Alpha Centauri, sits roughly 24 light-years from Earth. That means if you could travel at the speed of light, the absolute cosmic speed limit, the fastest anything in the universe can move, it would still take you more than 4 years to get there. And we cannot travel anywhere near the speed of light. Our fastest spacecraft, the Voyager probes launched in the 1970s, travel at roughly 35,000 miles per hour. At that speed, reaching Alpha Centauri would take approximately 75,000 years. And Alpha Centauri is our closest neighbor. The Milky Way galaxy contains somewhere between 100 and 400 billion stars spread across a disk roughly 100,000 light-years in diameter. The observable universe contains an estimated 2 trillion galaxies. And yet here we are, planning to go. Not planning idly. Not in the way that people in the 1800s might have fantasized about flying through the air, as a distant dream with no machinery behind it. We are planning with rockets and laboratories and billion-dollar budgets, and the serious, careful attention of some of the smartest engineers and scientists our civilization has ever produced. NASA is actively developing systems to return humans to the moon. SpaceX has built the most powerful launch vehicle in human history and has stated publicly that its purpose is to make humanity a multiplanetary species. The European Space Agency, China's National Space Administration, the United Arab Emirates, India, Japan. Nearly every major spacefaring nation on Earth is investing more in space exploration than at any point since the Apollo era. Private companies with names like Blue Origin, Rocket Lab, and Axiom Space are building the infrastructure of a space economy. Billionaires are going to space themselves, not as passengers but as architects of new industries. Something has changed. The question is no longer whether humanity will try to colonize space. The question is whether we will succeed, what it will cost us, who will be allowed to go, and what kind of civilization we will build out there, and what that civilization will do to us in return. To understand where we are going, we need to understand where we came from. The history of human expansion is, in one sense, a history of impossible journeys that eventually became possible. There was a moment in human prehistory. We are not certain exactly when, but probably around 50,000 years ago, when a small population of anatomically modern humans walked out of Africa and began moving across a planet they had never seen. They crossed land bridges. They built boats from materials they had never worked before to cross waters they had never seen. They walked into climates that were alien to everything their bodies had evolved to handle. They went into the cold. They went into the desert. They went onto islands that were invisible from the shore they left behind, guided by nothing more than the stars, the swell of the ocean, the flight patterns of birds, and an instinct for exploration that seems to be one of our most fundamental characteristics as a species. By the time the historical record begins in earnest, humans were already on every habitable continent. They had already discovered and settled every major island group in the Pacific. They had already developed dozens of distinct civilizations in isolation from one another. The drive to expand, to explore, to go somewhere new, this was not a late addition to human nature. It was there from the beginning. And then came the age of sail. Between roughly 1,400 and 1,700, European navigators sailed to every corner of the planet Earth. They mapped coastlines. They crossed oceans in wooden ships with no GPS, no radio, no satellite imagery, no ability to call for help if something went wrong. The mortality rates on these voyages were horrifying by modern standards. Scurvy, shipwreck, starvation, disease, these were not unusual fates for sailors of that era. They went anyway. Not all of them went willingly. The history of exploration is also, inextricably, a history of coercion and slavery and conquest, and the destruction of indigenous civilizations. We need to reckon honestly with that history, as we think about what it means to expand into space. But the drive itself, the need to go further, to see what is on the other side, that was real, and it was powerful enough to rewrite the geography of human civilization. Now we are at another such threshold. The ocean we are preparing to cross is not water but vacuum. The continents we are preparing to reach are not verdant and already inhabited but barren and alien and inhospitable in ways that make Antarctica look like a garden. And the tools we need to make the crossing are not wooden ships and cotton sails but rockets and life support systems and closed-loop ecologies and radiation shielding, and 1,000 other technologies that did not exist a century ago and are still being refined. The first destination is obvious. The Moon. It is the closest large body to Earth, averaging about 239,000 miles away, close enough that radio signals reach it in just over a second, close enough that we have already been there, close enough that our current technology can get us there in about 3 days. 12 human beings have walked on its surface. None of them stayed longer than a few days. The last time a human being stood on the lunar surface was December 1972, when Apollo 17 astronauts Eugene Cernan and Harrison Schmitt completed the last moonwalk of the program. For more than 50 years, the Moon has waited, untouched by human footprints. That is about to change. NASA Artemis program, launched in the early 2020s, is explicitly designed to return humans to the Moon and establish a sustained presence there. The program has already sent an uncrewed spacecraft around the Moon and back. It is planning to land the first woman and the first person of color on the lunar surface. And beyond the symbolic firsts, it is planning something much more ambitious. A lunar gateway, a small space station in lunar orbit, and eventually a base on or near the lunar South Pole that will allow humans to live and work on the Moon for extended periods. Why the South Pole? Because of water, or more precisely, because of ice. In the permanently shadowed craters near the lunar South Pole, where sunlight has not reached in billions of years, temperatures drop to around -250 degrees Celsius. In those frigid shadows, scientists have detected significant deposits of water ice. Water is the most valuable substance in space, not because humans need to drink it, though they do, but because water, when you run electricity through it, splits into hydrogen and oxygen. Hydrogen is rocket fuel. Oxygen is rocket oxidizer. A source of water on the Moon means a source of propellant on the Moon, which means that the Moon could become a refueling station for missions going deeper into the solar system. It also means the Moon could become a platform. Because here is the thing about the Moon that makes it so important as a stepping stone. Earth's gravity well is deep. It takes an enormous amount of energy to lift anything off the surface of the Earth and get it into orbit. That is why rocket launches look the way they do. The vast majority of the vehicle is fuel, and most of that fuel is burned in the first few minutes of flight, just fighting gravity and air resistance to reach orbit. The moon's gravity is only about 1/6 of Earth's. Launching from the moon takes far less energy. If we can build things on the moon, or refuel there, or use the moon as a construction site for vehicles that will never have to survive Earth's gravity at all, then reaching the rest of the solar system becomes dramatically more practical. The moon is also a laboratory. It has been sitting in the inner solar system for 4-5 billion years, largely unchanged, collecting cosmic debris. The rocks and soil of the moon contain a record of the early solar system that has been weathered away on Earth. Studying the moon tells us about where we came from. And there is something else. The moon contains helium-3, a rare isotope that is virtually non-existent on Earth, but has been deposited on the lunar surface over billions of years by the solar wind. Helium-3 is a potential fuel for fusion reactors, the clean, nearly limitless energy source that human civilization has been trying to achieve for decades. The amount of helium-3 on the moon, if fusion technology reaches the point where it can be used, could power human civilization for thousands of years. But the moon, even with all of this, is not the destination that captures the imagination the way Mars does. Mars is the real prize. Mars is where the serious long-term colonization talk is focused. And Mars is where the real difficulties begin to reveal themselves. Mars is, by any measure, a brutal place. Its average surface temperature is about -63 degrees Celsius. Its atmosphere is 95% carbon dioxide, with trace amounts of nitrogen and argon, and almost no oxygen. The atmospheric pressure on the Martian surface is less than 1% of Earth's, which means an unprotected human being on Mars would not merely suffocate, but would experience something closer to being exposed to the vacuum of space. There is no global magnetic field on Mars. The planet's core cooled and solidified long ago, and without a magnetic field, the surface is exposed to cosmic radiation and solar particles that would deliver lethal doses to any unprotected person over a time frame of months. There is also the dust. Martian dust storms are among the most spectacular weather events in the solar system. They can grow to cover the entire planet and last for months. In 2018, a global dust storm on Mars lasted for roughly 7 months and delivered so little sunlight to the surface that it ended the mission of the solar-powered Opportunity rover, which had been exploring the Martian surface for nearly 15 years. Dust on Mars is not just a nuisance. It is fine and potentially toxic, containing perchlorates that are harmful to human biology. It gets into everything. It coats solar panels. It clogs filters. And yet, Mars also has days that are almost the same length as Earth's. A Martian day, called a sol, is 24 hours and 37 minutes. It has seasons because it has an axial tilt similar to Earth's. It has a thin but real atmosphere that provides some protection and could theoretically be thickened over geological time scales. It almost certainly had liquid water on its surface billions of years ago. The evidence is written in its valleys and riverbeds and ancient lake basins. It may still have liquid water today, underground, kept liquid by geothermal heat or the salt content that lowers water's freezing point. And in those subsurface water deposits, or in the Martian soil, or in some sheltered crack in a canyon wall, there may be life, microbial life that has been surviving in Mars's underground for billions of years, retreating as the surface dried and the atmosphere thinned, clinging on in whatever refuge remained. The possibility of life on Mars complicates everything. If Mars has life, even microbial, even barely clinging to existence, then the ethics of colonization become extraordinarily complex. Do we have the right to terraform Mars, to fundamentally alter its atmosphere and temperature and chemistry? If doing so would drive a form of life to extinction, do we have the right to contaminate Mars with our bacteria and viruses and biological waste, potentially destroying the indigenous Martian biosphere before we even know it exists? These are not hypothetical questions. They are questions that astrobiologists and space ethicists are actively debating right now, and they do not have easy answers. If Mars does not have life, then the ethical calculus changes, though it does not disappear entirely. A dead world might seem like a blank canvas, free for us to do with as we wish. But even that assumption is worth examining. Even a dead world has scientific value in its pristine state. Even a dead world might be said to have some kind of right to its own character that we override at our peril. But let us set ethics aside for a moment and talk about engineering. Because before we get to argue about what to do on Mars, we first have to figure out how to get there and survive long enough to argue about anything. The journey from Earth to Mars, when the planets are favorably aligned, which happens roughly every 26 months, takes between 6 and 9 months depending on the trajectory chosen. 6 to 9 months in space is not like 6 to 9 months on Earth. Space is hostile to human biology in ways that are still not fully understood. Microgravity causes muscles to atrophy and bones to lose density. It causes fluid to shift toward the upper body, which changes the shape of the eyeball and can cause lasting vision problems. A syndrome now called spaceflight-associated neuroocular syndrome, or SANS, which is one of the more concerning health issues identified in long-duration spaceflight. It disrupts the immune system. It causes cardiovascular changes. It affects sleep. It affects cognition. The ISS has given us extraordinary data about what happens to human bodies in space over 6-month and 12-month missions. And what it tells us is that the human body was not designed for weightlessness. And compensating for that will require either medical interventions we have not yet developed or the creation of artificial gravity, which requires rotating structures and adds enormous complexity to spacecraft design. And then there is radiation. Inside Earth's magnetic field and underneath Earth's atmosphere, we are shielded from most of the radiation that fills the solar system. In deep space, that shielding is gone. Cosmic rays, high-energy particles that stream through the galaxy at nearly the speed of light, pass through spacecraft hulls and human tissue alike, damaging DNA and increasing cancer risk. Solar particle events, the massive eruptions of energetic particles from the sun, can deliver dangerous radiation doses within hours. Protecting astronauts from radiation on a Mars mission is one of the hardest unsolved engineering problems in human spaceflight. We can add shielding, but shielding adds weight, and weight is the enemy of spaceflight. We can use water as shielding. Water is actually quite good at absorbing radiation, but carrying enough water to shield a spacecraft requires enormous mass. We can design spacecraft that use their existing water supply and food storage as shielding. We can develop pharmaceutical countermeasures that protect cells from radiation damage. None of these solutions is yet adequate on its own. Probably some combination of all of them will be needed. Assuming we solve the transit problem, we arrive at Mars after 6 to 9 months and land on a world where everything that keeps us alive, air, water, food, warmth, pressure, must be manufactured or extracted from an environment that provides none of it in usable form. The habitat must maintain Earth-like pressure and atmosphere. It must have redundant life support systems, because if the CO2 scrubbers fail or the oxygen generation fails or the heating fails, people die very quickly. It must be protected from radiation, either by thick walls, buried construction, or natural shelter like lava tubes. It must be able to produce food, because resupply from Earth takes years and costs fortunes. It must have medical capabilities, because serious illness or injury on Mars cannot be treated with an emergency flight home. At minimum, any return to Earth would take months, and that is only if the planets are in the right configuration. During some periods of Martian orbital mechanics, a return window might not open for 2 years. This isolation is one of the most psychologically challenging aspects of Mars colonization. Astronauts on the ISS are 250 miles above Earth, close enough that an emergency evacuation, while dangerous, is possible. They can speak to their families in real time. They can see their home planet out the window. The psychological anchors are still there. On Mars, the communication delay alone, caused by the speed of light traversing the distance between the planets, which ranges from about 3 minutes to about 22 minutes each way, means that a real-time conversation with someone on Earth is impossible. A 6-minute round trip at best, a 44-minute round trip at worst. Emergency communication has this same delay, which means that mission control on Earth cannot guide a crew through a crisis in real time. The crew is on their own. They must make decisions. They must solve problems. They must keep each other alive without being able to call for help in any meaningful sense. The psychology of small groups in isolated, confined environments is well studied, and the conclusions are sobering. Conflict, depression, cognitive impairment, communication breakdown. These are documented hazards of isolation. Antarctic winter-over crews, submariners, and polar expedition members all provide data. The data suggests that group dynamics and individual psychology will be as challenging as any of the engineering problems on a Mars mission, possibly more so. So who would go? This is one of the more fascinating questions about the early stages of Mars colonization. The first settlers, and we should call them settlers, not just explorers, because the plan is not to visit and come back but to stay, will face conditions that make the most extreme environments on Earth seem comfortable. They will face physical and psychological hardship that cannot be fully prepared for on Earth. They will face the very real possibility of death from causes that range from equipment failure to medical emergency to simple accident, and they may face death with the full understanding that no rescue is coming. Elon Musk, whose company SpaceX is probably the most serious commercial contender to send humans to Mars, has said publicly that the first Mars missions will be dangerous, and that the early settlers should expect high mortality rates. He has framed this as acceptable, even noble. The comparison he most often invokes is the early European settlers in North America, who faced similar mortality rates and went anyway. The comparison is apt in some ways and deeply problematic in others, as we will come back to, but the underlying point stands. The first generation of Mars settlers will almost certainly lose some of their number. They will go knowing this. What kind of person goes to Mars under these conditions? Historically, the people who have volunteered for extremely dangerous exploration missions are not reckless thrill seekers. They are people with a specific combination of characteristics: high risk tolerance, strong sense of purpose, exceptional resilience, and a deep conviction that what they are doing matters beyond themselves. They are often people who feel more comfortable with extreme challenges than with ordinary life. They are often people for whom the idea of not going, of staying home, of playing it safe, would be its own kind of misery. In the initial phases of any Mars colonization program, the settlers will also be highly skilled. Engineers, doctors, geologists, biologists, psychologists, systems specialists of various kinds. People who can fix things when they break, diagnose illness in themselves and others, conduct scientific research with limited equipment, make decisions under pressure, and do all of this while living in a habitat roughly the size of a very generous apartment with the same 4 or 8 or 12 people for years on end. Over time, if the colony survives and grows, the composition will change. It will have to. 100 people is not a self-sustaining civilization. Even 1,000 people is not a self-sustaining civilization. Population geneticists have argued that a truly self-sustaining human population, one that could survive indefinitely without genetic input from Earth, requires somewhere between 10,000 and 160,000 individuals, depending on the assumptions made about reproductive rates and genetic diversity. Getting that many people to Mars is not a problem of the near future. It is a problem of the very far future, if it happens at all. But there is a middle stage between the first few dozen settlers and a self-sustaining civilization, and that middle stage is in some ways the most interesting and the most fraught. It is the stage in which a Martian colony is large enough to have its own social dynamics, its own culture, its own disputes and politics and identity, but still dependent on Earth for critical supplies and technology. This is the stage in which the question of governance becomes pressing. Who runs a Mars colony? In the early days, the answer is probably whoever paid for it. If SpaceX builds and operates the first Mars colony, Musk or his successors will likely have enormous influence over its rules. If NASA and its international partners build it, the governance structure will be more like the ISS, multinational, with elaborate protocols and chains of command that represent the interests of funding nations. But as the colony grows, as it develops its own economy and its own culture, as people are born on Mars who have never been to Earth and whose entire experience of life is Martian, the question of self-determination becomes unavoidable. The colonists on Mars will not be like colonists in any historical sense we have seen before, because the thing that makes colonialism on Earth so unjust, the displacement and exploitation of people who were already there, does not apply on Mars, unless Mars has life that we have failed to detect. But Martian colonists will face their own political dynamics. They will face the question of whether decisions made on Earth by corporations or governments that funded the colony should govern people who have built a completely different kind of life under completely different conditions. They will face the question of whether the laws of Earth's nations extend to Mars at all. The 1967 Outer Space Treaty, which governs the activities of nations in space, says that space is the province of all mankind and cannot be claimed by any nation. But the treaty was written before commercial spaceflight was a reality, and its provisions are being tested and strained by the commercial space age in ways its authors did not anticipate. There is an analogy sometimes drawn to the American colonies in the 18th century, the idea that a distant colony will eventually seek independence from the mother country that established it. The distance between Earth and Mars makes this analogy even more appropriate than it was for the original 13 colonies. With a communication delay of up to 44 minutes each way, a Martian colony cannot be governed in real time from Earth. It will, by necessity, develop its own decision-making structures, its own leaders, its own way of resolving disputes. Whether Earth accepts the political implications of that or tries to maintain control from a distance, with all the conflict that implies, will be one of the defining political questions of the coming century. But before we colonize Mars, and even as we plan the moon base, there is another space environment that deserves serious attention, and it is one that is far less glamorous but in many ways far more achievable in the near term: Earth orbit itself. The commercial space industry is already transforming low Earth orbit from a government preserve into an economic zone. The International Space Station has hosted more than 250 people from 20 countries since its first module was launched in 1998. It is scheduled to be deorbited sometime in the early 2030 and replaced by commercial space stations built by companies like Axiom Space and Blue Origin. These stations will be open to private citizens, space tourists, corporate researchers, government-contracted scientists, in a way the ISS never was. Companies are already sending private astronauts to the ISS for short visits that cost tens of millions of dollars per person. As launch costs continue to fall, driven primarily by SpaceX's reusable rocket technology, the cost of reaching orbit will drop, and more people will be able to go. In the longer term, there are serious proposals for permanent human habitats in Earth orbit, not just laboratories but actual residential facilities, places where people live and work for extended periods. The physicist Gerard K. O'Neill, working in the 1970s, designed what are now called O'Neill cylinders, enormous rotating space habitats, kilometers in diameter, that would use rotation to create artificial gravity and could theoretically house millions of people in Earth-like conditions. His calculations suggested that a pair of cylinders 10 kilometers long and 2 kilometers in diameter could house up to 10 million people each, with farmland, rivers, forests, and clear skies inside, powered by abundant solar energy, and built from materials mined from the moon or asteroids. O'Neill's cylinders remain theoretical, and building them would require industrial capabilities far beyond what we currently possess. But the underlying physics is sound, and the concept points towards something important. There is no reason why space habitats have to be small, cramped, dangerous places. Given enough time and resources, space habitats could be larger than any city on Earth, more comfortable than most places on Earth, and more sustainable than Earth's ecosystems. The energy available in space, from the Sun, which in orbit is not filtered by atmosphere and provides roughly 1.4 kilowatts per square meter continuously, is essentially unlimited. The materials needed to build habitats are present in the asteroid belt in quantities that dwarf Earth's available resources. The asteroid belt between Mars and Jupiter contains metallic asteroids whose iron, nickel, and platinum group metals, if captured and refined, would dwarf the total mineral wealth of Earth's crust. This is the vision that animates the most ambitious long-term thinkers about space colonization. Not just Mars, not just the Moon, the entire solar system as a resource base and living space for a human civilization that has outgrown its cradle. A civilization of perhaps trillions of people spread across habitats in the asteroid belt, the moons of the outer planets, the orbits of multiple stars. A civilization so distributed that no single catastrophe, no pandemic, no asteroid impact, no nuclear war, no runaway climate change could extinguish it. A civilization that is, in the most literal sense, immortal. This is also where the conversation about space colonization intersects with the deepest existential questions facing our species. Because one of the most powerful arguments for colonizing space is not about adventure or resources or political freedom. It is about survival. The Earth has been struck by large asteroids before. The impact that ended the non-avian dinosaurs 66 million years ago was caused by an object roughly 10 kilometers in diameter. Such impacts are rare on the timescales of human civilization, but inevitable on the timescales of geological history. The question is not whether Earth will be struck by a civilization-ending asteroid. The question is whether humanity will still be only on Earth when it happens. Similarly, The sun will eventually evolve into a red giant and swallow the inner planets. That is 5 billion years away, but it is coming. And on shorter timescales, centuries or millennia, human civilization faces potential disruptions from supervolcanic eruptions, extreme climate shifts, engineered pandemics, and other catastrophic risks, some of which we are creating ourselves. A species confined to one planet is existentially vulnerable in a way that a multiplanetary species is not. This argument, made most famously by Carl Sagan, and more recently by figures like Elon Musk and the philosopher Toby Ord, suggests that spreading humanity across multiple worlds is not merely adventurous but morally necessary, that we have an obligation to the future of conscious life to ensure it cannot be ended by a single event. This argument is powerful, and it resonates with something deep in human moral intuition. We instinctively feel that the extinction of humanity would be a catastrophe almost without parallel, not just for us but for the universe, because as far as we know, we are the only beings in the universe who are aware of it, who study it, who appreciate it, who tell stories about it. A universe without conscious beings to observe it is, in some profound sense, a universe that exists for nothing. To preserve consciousness, to ensure its continuation and flourishing, seems like one of the most important things we could possibly do. But this argument, like all arguments that appeal to the grand sweep of history and the fate of civilization, requires us to be careful about who benefits and who pays. Because space colonization is not free. It is not even cheap. The resources required to establish permanent human presence beyond Earth are staggering, and those resources come from somewhere. They come from budgets. They come from decisions about priorities. Every dollar spent building a Mars habitat is a dollar not spent on schools or hospitals or climate adaptation on Earth. Every hour of engineering talent devoted to rocket design is an hour not devoted to renewable energy or clean water or pandemic preparedness. This is not an argument against space colonization. It is an argument for clarity about what we are choosing and why. If we are going to colonize space, we should do it with open eyes about the trade-offs involved, about who makes the decisions, about whose interests are served, and about what values we want to carry with us. Because we will carry our values with us. This is perhaps the most important and least discussed aspect of human expansion into space. We will not leave our history behind when we leave Earth. We will take it with us, in our institutions, our biases, our habits of mind, our social structures. The question of whether a Martian colony will be a just and equitable society, or a hierarchy dominated by the wealthy and powerful, is not a question for the distant future. It is being decided right now by the people and organizations that are building the initial infrastructure of space colonization. Look at who is currently driving the space industry, and you see a pattern that should give us pause. The most ambitious programs are largely driven by private companies, led by extraordinarily wealthy individuals. Jeff Bezos and Elon Musk are the two most prominent, and both are building their space companies with explicit visions of what the future should look like. Visions that reflect their own values and assumptions as much as any universal human interest. The risk is that space becomes a new frontier not for humanity broadly, but for a new plutocracy. That the Moon and Mars become playgrounds for the ultra-rich, and places where labor can be exploited without the protections that centuries of struggle have created on Earth. This is not an inevitable outcome. It is a tendency that can be resisted. The Outer Space Treaty already forbids national appropriation of celestial bodies, though its provisions for commercial activity are less clear. International governance frameworks could be developed, and should be, to ensure that the resources of space are shared equitably, and that the societies built there meet basic standards of human rights and dignity. But these frameworks require political will, international cooperation, and a willingness to constrain private interests for the public good. These are not things that come easily. There is also the question of what space will do to us, not to our politics or our economics, but to our nature. What happens to a species that evolves over millions of years under a specific gravity, a specific atmospheric composition, a specific magnetic field, specific patterns of day and night and season, and then begins to live in environments that provide none of these things? What happens to children born on Mars, growing up under 1/3 of Earth's gravity, spending their entire lives in habitats rather than open landscapes, never having stood in rain or walked on grass or seen a sunset over an ocean? The short-term physiological effects of reduced gravity are documented. Bone density loss, muscle atrophy, cardiovascular changes. These happen to adults over the course of months and can largely be reversed by returning to Earth. But what about children who grow up in Martian gravity? Their bones and muscles will develop differently. Their bodies will be shaped by their environment in ways that may not be reversible and may not be compatible with living on Earth. A third-generation Martian, born and raised on Mars, might find Earth's gravity physically crushing, might be unable to walk in 1G without exoskeletons or medical support. They would be, in a very real physiological sense, a different kind of human being. Over many generations, natural selection might accelerate this process. Mars would favor certain traits: the ability to tolerate radiation, efficient oxygen use at low pressures, psychological traits suited to isolated small group living, intelligence for problem solving under constraint, and disfavor others. Height, for instance, is metabolically expensive and doesn't confer the same advantages in the confined spaces of a habitat that it might on the open plains of Africa where tall humans first evolved. Over thousands of years, Martians might diverge from Earth baseline humans in measurable biological ways. And beyond biology, there is culture. A community of human beings living on Mars will develop its own culture with remarkable speed. Cultures emerge from environments. The language, art, music, mythology, humor, values, and social norms of a Martian community will be shaped by the specific conditions of Martian life. By the color of the sky, which is not blue but a dusty pink or sometimes violet, by the rhythm of the Martian sol, slightly longer than an Earth day, by the experience of living always under shelter, never fully outside, always aware of the fragility of the systems keeping you alive. The culture of Mars will be unlike any culture that has ever existed on Earth, and it will be unlike Earth culture in ways that we cannot fully predict or imagine. This is both exciting and sobering. It is exciting because it means that human culture is not finished. The story of human creativity is not complete. New worlds will generate new art, new literature, new music, new philosophy, new ways of being human that we cannot conceive of from our position on Earth in the early 21st century. It is sobering because cultural divergence over time can become cultural conflict. Humans have a long history of treating people who are different from them, who speak differently, dress differently, worship differently, look differently, as lesser, as threatening, as enemies. The history of the meeting between cultures is full of beauty and full of horror in roughly equal measure. If Martians diverge from Earth humans over generations, culturally and eventually biologically, what will the relationship between Mars and Earth look like? Will it be a relationship of partnership, of competition, of exploitation, of war? Science fiction has explored this territory extensively, from the colonial allegories of H.G. wells to the detailed political futures imagined by Kim Stanley Robinson in his Mars trilogy. But fiction, however prescient, is not prophecy. What actually happens will depend on choices made by real people in real circumstances that we cannot fully anticipate. Beyond Mars, the outer solar system beckons. Jupiter's moon Europa is thought to have a liquid water ocean beneath its icy surface, kept liquid by tidal heating from Jupiter's massive gravitational field. The ocean of Europa may contain more water than all of Earth's oceans combined. And where there is liquid water and energy, on Earth at least, there is life. Europa is one of the most scientifically compelling places in the solar system, and a mission to drill through its ice and explore its ocean is one of the most ambitious ideas in space science. Saturn's moon Titan, with its thick atmosphere and lakes of liquid methane, is another extraordinary world. Enceladus, another moon of Saturn, sprays plumes of water vapor from its south pole, direct evidence of a subsurface ocean, and potentially hydrothermal vents where life might flourish. These are not places where humans could easily live. They are far from the sun, in environments far more hostile in some ways than Mars. But they are scientifically irreplaceable, and the question of whether life exists in their hidden oceans is arguably the most important scientific question of our time. Because if we find life on Europa or Enceladus, life that evolved independently of Earth, then the implications are staggering. It would mean that life is not rare, that it arises wherever conditions permit, that the universe is full of it. It would mean that the story of life is not the story of a single improbable accident on one small planet, but the story of a pervasive cosmic phenomenon. And if life is everywhere, intelligent life, over the billions of years, available for its development on billions of worlds around billions of stars, may be everywhere too. The question of extraterrestrial intelligence is the largest possible context for the question of space colonization. For a century now, humanity has been sending radio signals into space, first inadvertently as a byproduct of broadcast technology, then deliberately through programs like SETI and the messages encoded in the Voyager Golden Records. We have received no confirmed reply. The silence of the cosmos, what the physicist Enrico Fermi pointed to when he asked, "Where is everybody?" is one of the most profound puzzles in science. If the galaxy is old and vast and planets are common and life arises readily, as our best current evidence suggests, then where are the alien civilizations? Why haven't they made contact? The answers proposed to this question, known collectively as solutions to the Fermi paradox, range from the reassuring to the terrifying. Maybe intelligent life is rare despite life being common. Maybe technological civilizations tend to destroy themselves before they can colonize the galaxy. Maybe they are there but not communicating in ways we recognize. Maybe they are there, and we are being deliberately ignored. Maybe the universe is vast enough that even many civilizations produce no detectable signal across stellar distances. Maybe the Great Filter, some catastrophic barrier that prevents civilizations from expanding indefinitely, is behind us, baked into the improbability of our own emergence. Or maybe it is ahead of us, waiting. This last possibility, that the Great Filter lies ahead, is the one that keeps certain researchers awake at night. Because if something reliably prevents technological civilizations from successfully colonizing space, and if we are ourselves a technological civilization attempting to colonize space, then we are approaching whatever that filter is. We may be the test case. Our success or failure at establishing ourselves beyond Earth may be the answer to the Fermi paradox. This framing gives space colonization a significance that goes beyond human interest and touches the deepest questions of existence. If we are alone in the observable universe, or nearly so, then the stakes of what we do could not be higher. The preservation and flourishing of consciousness and intelligence might depend on us. If we are not alone, then how we behave as we expand into the cosmos, whether we go in peace or in conflict, whether we protect or destroy, whether we seek wisdom or power, will determine what kind of civilization we are in a context larger than human history. These are enormous thoughts, and it is easy to feel overwhelmed by them or to dismiss them as too abstract to be useful. But they matter. They matter because the decisions we make in the next few decades about how to govern space, about who benefits from its resources, about what values we carry into it, about how we treat other forms of life if we find them, will set trajectories that persist for centuries. There is a version of the future in which humanity successfully establishes permanent settlements on the Moon and Mars within the next 50 years, as several serious timelines project. In this version, the early settlements are small and difficult, but they survive and grow. Technology improves. Launch costs continue to fall. The knowledge base for living beyond Earth expands rapidly. More people go. Industries develop. Children are born off Earth. A Martian economy develops, initially dependent on Earth for technology and luxury goods, but increasingly self-sufficient as local manufacturing and agriculture advance. Within 200 years, the population of Mars is in the millions. It is politically independent of Earth, governed by its own institutions, culturally distinct, biologically diverging. The solar system becomes a civilization rather than a single inhabited world. There is another version in which it doesn't work out that way, in which the early attempts at Mars colonization fail catastrophically, not from one single disaster, but from the accumulated weight of 1,000 small failures. A habitat depressurization, a life support malfunction, a dust storm that lasts too long, a medical emergency with no treatment, a psychological breakdown in a critical crew member, in which the public and political will for space colonization evaporates after these failures, as it evaporated after Apollo, leaving behind a skeleton of infrastructure and a memory of ambition unrealized, in which climate change, geopolitical conflict, and the sheer difficulty of solving problems on Earth consume all the energy and resources that might have gone to space, leaving the stars as beautiful and unreachable as they have always been. Both of these futures are possible. Neither is inevitable. What separates them is not physics or engineering. The physics and engineering are within our grasp. What separates them is will. The collective human decision, made again and again over decades, that this matters enough to keep trying, that the investment is worth making, that the risk is acceptable, that the difficulties, as great as they are not greater than the dream. And here we come to what may be the most fundamental question about human space colonization, not whether we can, but whether we should. Whether the impulse to go to the stars, which feels so deep and so natural to so many of us, is a virtue or a flaw. Whether the species that has so thoroughly transformed, and in many ways damaged, one world should be trusted with the tools to transform others. This question deserves a serious answer. The case against space colonization is not ridiculous. It rests on the observation that human expansion on Earth has generally been bad for existing ecosystems and existing inhabitants, that we have not yet demonstrated the wisdom to be good stewards of what we have, and that the resources devoted to space would be better used addressing the suffering that exists right now on Earth. These are legitimate concerns. They deserve to be heard. But the case for space colonization is not merely about adventure or escape or greed. At its deepest level, it is about the nature of life itself. Life, as we understand it, is characterized by a drive toward expansion, toward filling available space, toward exploring every niche that can be reached. This drive has been the engine of evolution and the engine of human history. To suppress it entirely, to decide that Earth is enough, that we will stay here and work only on what we have, would be a choice unlike any our species has made before. It is possible to make that choice, but it would require understanding ourselves in a way that may be beyond us. There is perhaps a third path, not the path of conquest and resource extraction that characterized terrestrial expansion in its worst moments, and not the path of paralysis, waiting until Earth is perfect before we look outward, but a path of conscious, careful, ethically informed expansion that carries with it the hard-won knowledge of what we have done wrong, that builds in protections for other forms of life, that distributes its benefits widely rather than concentrating them in the hands of the few, that goes to space not to escape Earth, but to extend what is best about it. This is the path that is worth fighting for. Not the space colonization of empire, but the space colonization of maturity. Not the space of billionaires extracting resources and planting their flags, but the space of all of humanity, represented in its full diversity and complexity, reaching together into the unknown with the hard-won wisdom of a species that has made terrible mistakes and is trying, imperfectly and persistently, to do better. The children being born today will live to see human beings return to the moon. They may live to see the first human footprint on Mars. Their children may be born on other worlds. The universe is very large, and we are very small, and we have barely begun. But beginning is everything. The first step out of Africa was very small too, and look how far it led. Every great journey in human history has begun with someone standing at the edge of the known world and deciding to take one more step, into the forest, into the ocean, into the sky, and now into the dark between the stars. We do not yet know what awaits us there. We do not know if we will find barren silence or teeming life, terrible danger or unimaginable beauty, resources that could enrich all of humanity or challenges that will break us. We do not know if we will find in ourselves, when tested in that ultimate laboratory of the cosmos, the wisdom and courage and compassion to become the species we have always imagined we could be. But we are going to find out. That much seems certain. The rockets are being built. The plans are being made. The countdown has already begun. The question now is not whether we will go to space, but who we will be when we get there. And the answer to that question is being written right now in the choices we make, the values we hold, the futures we build here.